Pool players often pride themselves on their ability to impart a large speed to a pool ball. In the sport of billiards, event organizers often remove one of the rails on a pool table to allow players to measure the speed of their break shots, the opening shot of a game in which a player strikes a ball with his pool cue. With the rail removed, the ball can fly off the table as shown in the figure. The surface of the pool table is a height of 0.71 meters above the floor. The winner of the competition wants to know if he has broken the world speed record for the break shot of 32 miles per hour, which is about 14.3 meters per second. If the winner's ball landed at a distance of 3.65 meters from the table's edge, calculate the speed of his break shot V0. Assume friction is negligible. This is a relatively standard what we've been calling cliff running shot, because the ball leaves the table horizontally at some speed V0. And to make it look like our earlier problems, I'm going to rename this R. That doesn't really change anything, of course, but it allows us to use our earlier results to at least look at them. So, in fact, I'm going to redraw the whole thing and go to a different page so I can have more room to write. So here we have our pool table and our height of h, and the ball falls down like this, and a speed of r, or sorry, a range of r with a speed of v0. And we know our two moments that we're going to care about are going to be t equals 0 here and t equals the time of flight there. So let's start with that. We'll put our origin directly below the pool ball right as it leaves out here, with that's plus and that's plus. And so we have that. We have x is x initial, which is 0, and y is y initial, which is the height h. And then it lands, x is x final, which is r, and y is y final, which is 0. But of course, additionally, the ball leaves the table with v is v initial, x, which we're calling v initial, that's vx, and vy is v0y, which is 0. And then it lands with vx equals vfx, which I don't know, and vy is v final y, which I also don't know. And then we should look at this and we say, well, in the first part, we want to find this, and in the second part, we want to find these, so we can find the total speed. Just before impact, in fact, let's draw that by saying it lands here with some speed v1, so I guess we'll call these v1x and v1y. All right, this at first looks a lot like our earlier problems. We have a time of flight that we don't know, but if I get the time of flight, I can plug it in to get there. And that's the first thing I'm going to do. So I'm going to say, using the y equation, we have y equals y initial plus v initial in the y times the time, plus 1/2 times the acceleration in the y, which is g downward, times t squared. And of course, we'll have that x equals v0x plus, well, times t. Those are our two equations. Add a room here, so I'm going to pop to another screen. So we have, for the time we have at the end, we have the distance traveled is v0 times the time of flight, and also 0 equals h minus 1/2 g tf squared. And as we solved several times in class, this eventually becomes that the time of flight is the square root of 2h over g. Which we can throw in numbers to get some facts on. This is the square root of 2 times 0.710 meters over 9.8 meters per second square. All of that square rooted, so the time of flight turns out to be 38065. I'm carrying way too many sig figs here because I'm going to be using that as an intermediate number, so I have to keep up with that. We can take that time and put it in here to say that the actual speed is the range traveled over the time taken, and for us that ends up being 3.65 meters over 0.38065 seconds, which turns out to be 9.588 meters per second, which probably should round it to 9.6. Sadly for this person, they did not break the speed record. Now we want to find the speed v1 that it hits the ground. So something like this, and we're going to do it by finding the two components, which are I'm going to call v1x and v1y, because this thing is v1. And I'm going to use my various equations I have from earlier. Well, v1x is just v initial x, is just v0, is the whatever 9.59. Because there's no horizontal acceleration, so it keeps going at the same speed. v1y is a little weirder. It's v initial y plus the acceleration times the time. So, well, we know that this was 0, so I didn't really have to put that there. So we get something like minus GTF, which is minus 9.8 meters per second square times 0.380. Oh, that's terrible. Sorry. Let's do this over here. Minus 9.8 meters per second square times 0.38065 seconds, which is something like minus 3.73 meters per second. But we have to be careful because neither of those are actually what we wanted. We want the actual speed. So we back to here and we say, remind ourselves that we want v1, and we were given, we want v1x and v1y. But that's pretty easy because we can see that v1 squared is going to be the sum of v1x squared plus v1y squared. That is just going to be Pythagorean. And so I can just grind that out and find that v1 is the square root of 9.59 meters per second quantity squared plus negative 3.73 meters per second squared. Word to the wise, definitely put this in parentheses if you're going to put the minus sign in. Otherwise, it will evaluate the difference rather than the sum of those squares, and that would be bad. Or you could just remember that since it's going to square out anyway, you don't actually have to put the minus sign at all. We end up with 10.2898 meters per second, which is definitely too many sig figs, but it looks like it probably should be 10.3 meters per second. Actually, it's funny because the book carries 4, so I guess they really want it to be 10.29 meters per second.